Good morning everyone. Welcome to today's class. Today we are dealing about some more theorems about the separation axioms. 2.7 proposition. Let X be a regular space, C a closed subset of X, and capital F a compact subset of X such that C intersection F is equal to empty. Then there exist open sets U and V such that C is contained in U, F is contained in V, and U intersection V is empty. This we can prove in this way. Suppose you got a topological space and F a compact set and your C as a closed set. Now in F we will have the members and you will have the members some X and some X and Y and Z. I'm taking only a finite number of elements because we have seen that in whenever F is compact, every open cover of it should have a finite subcover. So if I am having some open cover of this by Vx1 or V, suppose I am having a finite subcover, a open cover of Vxi, then it should have a finite subcover, means I can find some V x1 x2 comma Vx2 etc. I'll go for up to some finite number, so V some xn. So I can consider only this point x1 x2 etc xn. For the time being I am considering only 3 points x, y and z. So I'll press this. Now here got we should consider only these 3 points. 3 points. And since the space is a regular space, we can separate these points and your closed sets. So if I am taking like this, I can have an open set containing X and an open set containing C. And again, I can go for the open set containing Y and the open set containing our C. And again, I can go for some open set containing Z and the open set containing C. So in each case, if I am naming this as Ux, Uy, Uz, then take the union. I will get a set U. It should be open. Now here you can go for the intersection. If this is V1, V2, V3 means go for the intersection. Then evidently you will get two open sets such that the intersection is empty and you can have C is contained in U and F is contained in V. So 2.7 proposition. Next theorem. Every regular Lindelof space is normal. Every regular Lindelof space is normal. Lindelof means if a space have every open cover of a space has got a countable subcover then we will say that the space is Lindelof. So we want to prove that every regular Lindelof space is normal. So in order to prove the normal condition, we want to take two closed sets. So suppose X is a regular space and C and D be disjoint closed subsets of X. We assume that X is regular and C and D are disjoint closed subset of X. Now, by characterization of regularity by proposition 1.15, we've seen that it's equivalent to say that for any x belongs to X, G containing X, there exists an open set H containing X such that H closure is contained in G, or which is equivalent to the family of all closed neighborhoods of any points of X form a local base at that point. So we will use here this condition. That means for x belongs to X, an open set G containing X, there exists an open set H containing X such that H closure is contained in G. So we get for each x belongs to C, an open set Ux containing X such that Ux closure is contained in X minus D. D is open, so X minus D is closed, so we can have this condition. Sorry, D is closed, so X minus D is open, so we can go for this condition. And similarly, for each Y belongs to D, an open set Vy containing Y such that Vy closure is contained in X minus C. Now the sets C and D are closed subsets of a Lindelof space. And we know that closed subset, Lindelof and compactness are weakly hereditary. So it will form a C and D will be a Lindelof spaces. So the open covers, we can consider the open covers of Ux and Vy, where Y belongs to D, of C and D respectively, have the countable subcovers say Un and Vn, where n is running from 1, 2, 3, etc. Now from our previous experience, we may have a tendency to take one as to be the union of such UNs and another one union of Vn. Then we can have these two open sets separating open sets. But this is not the fact now. Since suppose we are taking U like this and V like this. See this we are following from, see here and on we can take the union, here the intersection and go for such two open set. But here the story is something different. See, unfortunately, UN closure is contained in X minus D for N. But we cannot deduce from it that U closure, that is, its union is closure is contained in X minus D. Because the closure of U may larger than your union of such closures. That means finding union your n equal to 1 to infinity, you're going for un. Now, and we are finding this all closure. Sometimes these two may not be equal. So, this may not be equal. So, we will have a, we will use a trick here. Now for each n belongs to n, let Gn equal to un minus union I equal to 1 to n of Vi closure. and Hn equal to, we will consider Gn and Hn. Hn equal to Vn minus union I equal to 1 to n ui closure. Now Gn and Hn are open sets. Now G can be written as union of Gn and H can be written as union of Hn. Now we claim that C is contained in G. For X belongs to C, let X belongs to Un. Because X belongs to C means Un will cover C. So X belongs to Un for some n. Also X does not belongs to Vm closure for all m since Vm closure is contained in X minus C for all m. Hence X belongs to Gn. Since Gn we have defined as Un minus union I equal to 1 to n Vi closure. Now we have seen that this X does not belongs to any of this Vi closure. So there is supposed so X should belongs to Un minus this thing. That means X belongs to Gn. Now if X belongs to Gn means you are taking the union of such Gn as G. So your X should belongs to G. So we proved that C is contained in G. You have taken an X in C and you have got X in G. So C is contained in G. Now similarly you can prove that D is contained in H. Thus G and H are open sets in X containing C and D respectively. Now to complete the proof, what we want to show is these two open sets are disjoint, that is G intersection H is empty. Suppose not, then there exists some M and N such that GM intersection Hn is non-empty. Now we will assume that this M is less than N. We will have some GM intersection Hn is non-empty and we will assume that this M is less than N. Now let X belongs to this intersection, that is GM intersection Hn. Then X belongs to, it belongs to GM. GM means we have taken GM as UN minus this. So an element belongs to Gn means that element may belongs to any of this UM. So like where we are taking, so X belongs to UM, but UM are open sets. So this may contain in UM closure, which contradicts that X belongs to HM. Because you are taken in the intersection. So X belongs to GM and X belongs to HM. But here you are seeing that X belongs to UM closure. But HN you have considered as Vn minus of UI closure. So here you have got some closure. This closure is certainly will be a member in this. So you are avoiding that elements from your Vn. So it cannot belongs to your Hn. So you are getting a contradiction, which contradicts that X belongs to Hn. So H intersection G should be empty. So this is the condition what we proved for normal. That means if you are having two closed set, there exists two open disjoint open sets such that one closed set is contained in one open set and another open set is another closed set is contained in next thing. Now a corollary, 2.9 corollary. Every regular second countable space is normal. Every regular Lindelof space is normal, that we proved. Second countability means it is Lindelof. So the proof follows from the previous one. Second corollary, every compact Hausdorff space is T4. Every compact Hausdorff space is T4. Now by theorem 2.6, every compact Hausdorff space is regular. So this is a regular space, and hence by 2.8 it is also normal. That means just before you have proved that. So compact means is going to be a Lindelof one. So every Lindelof regular space is normal. In the same way you can prove. And moreover, it is a T1 space. Since it is a Hausdorff means it is T2. T2 implies T1. Now putting all this together, we will get a compact Hausdorff space is T4. For T4 condition, we want to have normality plus T1 condition. From this, you have got the normality, and from here, you have got the T1 condition. 2.11 theorem. A and B be compact subsets of topological spaces X and Y. Let W, see, let W be an open subset of X cross Y containing the rectangle A cross B. Then there exist open sets U and V in X, Y respectively such that A is contained in U, B is contained in V, and U cross V is contained in W. To understand this one, we can consider your R1 and R2. That means when you're taking cross, the, when you're taking cross, you can go for this here, one R, and here is one R. So this is met your R2 plane is nothing but R cross R. So A and B be compact subset of a topological space X and Y respectively. So this is your X and this is your Y, and we want to go for the compact subset. Compact subset means A and B, right? So in A and B means we can go for closed sets. So it's nothing but intervals, closed intervals. So this is where suppose we are taking like this. So this set is your compact subset. So let me mention this as your A and this as your B. Okay. Subsets of a topological space X, Y respectively. Let W be an open subset of X cross Y containing the rectangle A cross B. So the rectangle means, yes, if you are having this, if we are extending this, and extending this and this, we'll get some rectangle here. Something like this. So this is your set A cross B. Set A cross B. Now, see, uh, subset of X cross Y. We want to take W be an open subset of X cross Y containing the rectangle A cross B. So here I am considering another open set containing W. So open set containing W in R2 you can go for something like this. So this is an open set containing your A cross B. Then there exist open sets U and V in X, Y respectively such that A is contained in U and B is contained in V. It's evident. Since we are going for this extension, you will get somewhere here and here some open set. Now if you're having going for here, from here and this point somewhere here, see, now you can have an open interval which containing A. Here also you have got an open interval containing B. So U and V are open sets in X and Y respectively such that A is contained in U, B is contained in V, and U intersection V is contained in W. See, this U intersection V means exactly you get here a rectangle. See, you can go for this little more finer, then you can have exactly the rectangle. I delete this, 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 and this. Okay, so if I am going for I can have an open set something like this. Okay, so this is my open set. You can go for the open sets. So let's see. I'm making, yeah. Now I can have from here I can go for here. From here I can go for here and here and here. See, it's coming here. So if I am making here, I will get exactly a rectangle. See, I want to take and U cross V. So this is my U red marked one and this is my V. So when I'm taking U cross V means I will get something here. Some rectangle over here. Only I will get. So this is U cross V is contained in W. So the U cross V is contained in W means you have taken open subset of O. Sorry. So the other way, you're having A cross B, then you're having the cross as everything seems okay. So you have got a rectangle A cross B over here and an open set containing this one. Then evidently you can go for somewhat bigger one, that is again another rectangle which containing your set. So it is on this way. So this is your U cross V and this is your W and this is your A cross W. Sorry, A cross B. So the proof is if A or B is empty, so the result is very trivial. So we will assume that A and B are non-empty. Now take an element B belongs to B and fix it. For each A belongs to A, W is an open neighborhood of the point AB. This W is an open set containing, so W can be taken as an open neighborhood of the point AB belongs to X cross Y. Now by definition of product topology, there exists open set GA and HA in X cross Y respectively such that A belongs to G and B belongs to H. Therefore, GA intersection HA is contained in W. Here, G and HA depends only on A, in the sense that we have fixed B. Exactly, it will depends on A and B, but since B we have fixed, we are taking only in terms of A. Now the family GA, A belongs to A, is an open cover of the compact set A. Since A you are taken from A and you are taking all the open sets containing such A's, so it will form a open cover of compact set A. So it should have a finite subcover. That finite subcover is GA1, GA2, etc. GAN. Now let GB is equal to union of such GAI and HB is equal to intersection of HAIs. Now GB and HB are open sets in X, Y respectively, such that A is contained in GB and B belongs to HB, and GB cross HB is contained in W. Now this set depends only on points B. Up to here we have used only the compactness of A, but compactness of B we haven't used. So for each B belongs to B, we define open set GB and HB as above. Now the family HB, B belongs to B, is an open cover of B, and B is compact. Since B is compact, this should have a finite subcover. So that finite subcover is HB1, HB2, etc. HBM. So this is the finite subcover. Now let U is equal to intersection of let GBI and V is equal to union of HBI. Thus U and V will be the open sets with our desired properties. That means U and V open such that A is contained in U, B is contained in V, and U intersection V is contained in W. So in the figure, U intersection V is contained in, so W is bigger. So I should rename is, this is not W, this is your W, right? Sorry for the misinterpretation. So this is your U intersection V. So U intersection V is contained in W. Now 2.12 proposition. Let X be a completely regular space, and suppose F is compact subset of X. Here I have made mistake in your picturization. So if you need a neat one means you can erase everything. You can go for a neat one. Okay. Yeah. Here first of all you have got you can take going for R cross R. Make picture here. Here having one R. So not here. we got another R. So this is R cross R. From that R cross R, you want to consider two compact subset. So two compact subset means it should be closed intervals. So one closed interval here and one closed interval here, one closed interval somewhere here, and one closed interval here. Now when you're taking this cross means you will get exactly somewhat a rectangle. So this is my, oh sorry, so I will get exactly as what a rectangle. So the rectangle may come somewhere here. This may be your rectangle. This is your uh, x cross y. Sorry, a cross b. So this is your a, this is your b. So this will be your a cross b. Now W be an open subset of x cross y containing the rectangle a cross b. So we go for W as a bigger open set. Okay, I will take W. So this is your W. Okay. Now what we have is open subset of x cross y. In x cross y we are taking r cross r, so it should be an open disk. Now containing the rectangle a cross b, that is satisfied. Then there exist open sets U and V in X and Y such that A is contained in U and B is contained in V and U cross V is contained in W. So here you can go for, see, you are having an open set here, open set here which containing A, and here also an open set containing B. See, now if you are considering this open set, so this is making as U and this I'm making as V, you go for U cross V. So when I am going for U cross V, I will get again a rectangle. Uh, yeah. Now this U cross V is contained inside your W. So this is my set U cross V. So this U cross V is completely contained inside your W. Now the picture is clear. Now we are going for next proposition. Let X be a completely regular space and suppose F is compact subset of X. X is completely regular, F compact, and C a closed subset of X, and F intersection C is empty. Then there exists continuous function from X into the unit interval which takes the value 0 at all points of F and the value 1 at all points of C. This is somewhat similar to a completely regular condition, but in completely regular condition you are taking two closed set, a point and a closed set you are taking in completely regular case, but instead of a point now you are taking a compact set. So X be a completely regular space, then Proof is very simple it seems, since in F is compact means you can take any elements of F as x1, x2, x3. If you're taking some x1 and this uh, closed set C, you can have a function. Now, if you're having, since it's completely regular, you go for x2 and this closed set, you have another function. Okay, like that. So, if f is empty set, the function is identically equal to 1 will work. Because we want to take the value 1 at all points of C. So f is empty means there's nothing to prove. Similarly, if C is equal to empty, the identity function 0 will work. So let us assume that both f and C are non-empty. For each x belongs to F, there exists a map fx from x to close level 0, 1. This I have said earlier, such that fx of x is equal to 0 and fx of y is equal to 1 for all y belongs to C. This is because we are given that the space is completely regular. So if the set f were finite, we could easily get the result by taking the minimum or the product of the finite family of functions fx. Since previously we are taking open set and you are going for this intersection and union. Here we are having functions. So we have to go for the product of that or the minimum of that. Since f is compact, for each x belongs to f, ux be the set fx inverse of closed level 0, 1 by 2. Then ux is an open set containing x. So the family, because you have taken fx as 0, so it will belongs to this category containing x. So the family ux, x belongs to f, is an open cover of the set f. Now by compactness of f there exists finite subcover. So the finite subcover is ux1, ux2, etc. uxn. Now define f from x to close level 0, 1 by f of x is equal to minimum of this fx1, fx2, fxn, x. Now for x belongs to x, f is continuous and you're taking the minimum of a continuous functions. Also, this f assumes the value 1 at all points of C. Reason is fxi of x is equal to 1 for u belongs to or x belongs to C. However, this f may not vanish identically on f. Now we can correct that as we know that f of f is a subset of the semi-open interval 0, 1 by 2. Since for x belongs to f, there exists I such that 0 less than or equal to fxi less than 1 by 2 and f of x is less than or equal to fxi of x. Now let g be a continuous function from the unit interval closed level 0, 1 into itself. Let g be a continuous function from the unit interval closed level 0, 1 into itself such that g of closed level 0, 1 by 2 is equal to singleton 0 and g of 1 equal to 1. Next we can let g of t is equal to 0 for 0 less than or equal to t less than or equal to 1 by 2 and g of t is equal to 2t minus 1. So 1 by 2 less than or equal to t less than or equal to 1. Now the composite G composition F vanishes identically. So G composition F. So G composition F of t means G of F of t will come. What is F of t? it is fxi of x. So fi of x means is equal to 1 for x belongs to C. So, and fi of x is 0 for x belongs to F. So, we will have two open sets. Or sorry, we will have a continuous function as G composition F. Now, the remaining thing I'm leaving you to read. That means the saturated set definition and some of the properties of saturated sets. Lastly, a subset S of X is said to be saturated with respect to decomposition D if P inverse P of S is equal to S. Okay, you should read this one. Definition of saturated set and some properties of saturated set is given. Go through it. Any doubt means you can ask. I'm winding up today's session. Thank you. Thank you.